So this is ECE 343, Signals and Systems, third part of Chapter 1. In the first two parts of Chapter 1, we talked about signals, the description and properties of signals. In this particular part, we're going to transition and start talking about systems. A system is an object or device that takes an input, processes it, manipulates it, changes it to create an output. To give a quick example system, let's take a look at a GPS receiver. A GPS receiver ends up collecting signals from space. In this particular case, I've shown a satellite sitting out there in space, satellite 7, so S7. It has a particular unique code. I've drawn that as a bunch of ones and zeros. By the time it reaches the GPS receiver, it's gone through the Earth's atmosphere. That ends up getting distorted or having some noise added onto it. So the GPS receiver input is a noisy version of that satellite code. Within the GPS receiver itself, this thing that we call a system, it takes that input, processes it to generate some outputs. In this particular system, I've shown multiple outputs. I've shown one, that's the output of detector 1. The whole job of detector 1 is to say, is satellite 1 out there? I went all the way through and looked at then the output of detector 7. Detector 7's basic job is satellite 7 out there? In this particular case, we know that satellite 7 is out there. The GPS receiver did its job. It did detect it by showing a spike in the output. So what's a system? A system is something that operates on an input signal to generate an output. We can provide a little bit more mathematical idea to these ideas, or mathematical description to these ideas. So let's recall very quickly that a signal is a mapping. We had seen this before in an earlier part of our Chapter 1 discussion. It takes an independent variable t, right, and it maps it to a dependent variable x. So signals are mappings where they take an independent variable t and map it to a dependent variable x. A system, mathematically, is also a mapping. So we can look at the system as also being a mapping. But instead of taking the independent variable t, it takes an entire function, which we call the input function, and it maps it to another entire function. We call that the output function y. So both signals and systems are mappings. A signal maps an independent variable t to a dependent variable x, and a system maps an input function x of t to an output function y of t. We're most interested in systems that can be represented mathematically. That's obvious in the reason that we want that. If we can do it mathematically, we have a chance of being able to design system and understand systems in a very precise and reproducible way. For now, we're going to go ahead and focus on what are called single input, single output systems. They sometimes abbreviate this as SISO or SISO. If you go back to the previous example I gave, this was not an example of a single input, single output system. This one had a single input that was whatever was the received signal, but its outputs corresponded to all the different detectors. So at least as drawn here, it showed a total of at least 7 detectors. So this would have been a single input, multiple output system. For just simplicity in this class, and because you can't really understand the other cases until you get this first case, we'll simplify or at least restrict our attention to something called the single input, single output. What is a single input, single output system? We only have a single input function x of t. The system operates on that and it generates a single output function y of t. We'll go ahead and designate our system as a box. We'll use a letter, lowercase h or uppercase h are both common in this book, to designate that system. And if we were going to begin our mathematical description, then we might do something like this. We might sit there and say the output y, right, is equal to the input x operated on by that system h. I'm going to do a little bit more careful notation that maybe is found in the book. When I throw in that system h, operating on that input x of t, I'm going to go ahead and use curly brackets in here. So that curly bracket idea is going to be kind of your indicator that this is a system operating on something. So if I was going to read this out, I'd say the system output y is equal to the system h operating on the input x of t. We can designate this input-output relationship from a system in a little more compact form. This is called the directed arrow notation. So I have an input x of t, always, almost always, just by convention, shown on the left, generating an output y shown on the right, and I just use an arrow to connect the two, and that arrow designates the operation of the system, and sometimes they'll put a letter either above or below the line indicating that system itself. So H in this particular case. This would be read as input X going through system H to generate output Y. Now that we know the basics of what is a system, we're going to turn our attention to looking at some system properties. These system properties are really important for us in our study of signals and systems because systems with particular properties enjoy certain mathematical descriptions and understanding input and output. It gives us some ability to handle those things mathematically. The most generic, the most general kind of system like I've drawn here, where we just say an output is generated from an input, is so generic at this point that it's really not terribly useful. If we have a few properties, though, we'll find out that we're going to be able to make a lot more precise and understandable relationships between input and output descriptions. So let's go ahead and look at some system properties. The first one, in fact, the first two I look at are probably the most important, but let's start with linearity. So linearity is a system property, and really linearity is connected to the idea of superposition. You've probably seen linearity before in one of your previous classes like circuits. The superposition property does what? It basically says linear combinations of inputs generate the same linear combination of outputs. If I wanted to write this mathematically, I might do it something like this. I might say something like if input x1 of t generates an output y1 of t, and x2 of t generates an output y2 of t, then a linear system would be one that the input ax1 of t plus bx2 of t will generate an output what? Well, the input here now, the modified input, is just a linear combination of these other inputs. It's sum of scaled versions of inputs, ax1 plus bx2. And if linearity holds, well, then the output would be the same linear combination just of the outputs. So that would give us an ay1 of t plus by2 of t. So if I scale an input, I just get a corresponding scale on the output. If I add two inputs together, I just get their corresponding outputs added together. Linearity is a principle of superposition. It has both the additivity property, that's the addition part, and it has the scaling or homogeneity property, that's the multiplying by some scale constant on the input, giving us the same multiplication by scale constant on the output. There are some other ways of looking at this. I've shown a more mathematical description. If x1 goes to y1 and x2 goes to y2, then ax1 plus bx2 goes to ay1 plus by2. If you can show that's true, then you know it's linear. It can also be looked at from a graphical standpoint. So the graphical standpoint says something like this. It says, if a system is linear, if a system is linear, right? The system itself, H, commutes. It commutes with summation and scaling. We haven't gotten to the graphical part. We're going to do that now. So what does commuting mean? It means order doesn't matter. So it's saying the system and the operations of summing and scaling can come in either order and still give you the same result. How might we look at this? We might look at it in the following way. If I have an input x1 of t and it goes through a system H, right? We know that what comes out, that's its corresponding output, y1 of t. And if I had x2 of t going through a system H, right, it would generate some y2 of t. Then what am I going to do with these guys? I'm going to take these guys and multiply them by some a and some b, and then I'm going to add those results together to get some total response, y total. Let's call it y total of t. So I run my inputs through the system, and then I do my scaling and summing, right? So if I take a look in here, I have the system shown here first, right? System shown here first, and then I've got my summing and scaling, something along those lines. If something commutes, right, that means I can interchange the order. So that would look something like this. I would have x1 of t going through my scale factor A, and I would have my input x2 of t going through its scale factor B. Go ahead and add those guys together. That's like that modified input that we had seen before, right? And then we're going to go ahead and run that through the system H, something like that, right? And we should get out another total response. You know, I probably could have done a better job on this other one. Let's go ahead and change that output just a tiny bit. Let's go ahead and draw that as just the direct thing that it says in there, ay1 of t plus by2 of t. This other one, we had what? We had an ax1 of t plus bx2 of t. That's feeding into our system, and we're going to get some y total of t coming out of there. If the system is linear, right? So if the system is linear, this first combined output would need to be equal to that second. So this is equal if H is linear, right? It says that we can scale in some of our inputs, feed it into the system, and that output would be the same as if I had the outputs of each system summed and scaled using the same linear combination. That idea of superposition is also an idea of commutability. The order of operations, system and summing and scaling, can be interchanged without affecting the output. So that's a graphical way of looking at linearity. For linear systems, we can say a few things. So for linear systems, we know a couple things. For example, we know that in the total response, the y total, the total response of a system can be thought of as the output of two different parts, which I'll try to explain here in a minute. So there's going to be a YZR and there's going to be a YZSR. So the ZSR is the zero state response, zero state response. And YZR is the zero input response. So let's think about this just a little bit. When you think about a system and how it generates an output, how does it generate an output? The energy has to come from somewhere, right? And really there's two ways that a system can generate output. It can either have energy already stored in the system, which generates the output, or you externally apply energy to the system through an input, right? And that generates an output to the system. Think of a simple case of a circuit. I could have in here some sort of an input, right? And it could be feeding into a resistor and a capacitor, something like that. And we could be monitoring the voltage on that capacitor as my output. What are the different ways that I could have some output, right? Well, I could have stored originally some charge on that capacitor, even if I had no input at that particular case, right? That stored charge on the capacitor would cause that guy to discharge through the resistor, right? An initial storage of charge on the capacitor bleeds off through that resistor, generating an output because I already had energy in the system. This one, right, is a zero input response, so that's YZIR. It is an output in response to energy that was stored inside the system. I could also go through there and think about there being no charge, right? No charge on that capacitor. It just came out of the shop. We just plugged it into this thing, and then I applied some voltage source. Maybe I put in there a DC voltage. I could put in something like a 9-volt battery, something like that. What is the way that the output looks in that case? You had a discharge capacitor and you applied a battery to that guy. We're going to end up seeing that voltage on the capacitor is going to charge up to whatever that battery level was, 9 volts in this particular case. This guy is the zero state response. When we talk about the state of a system, we're talking about internally stored energy, at least at the initial starting point. So if it's zero state, it means there is no energy in it. The zero input means there was no input on it, right? So there's two sources of energy that can generate an output: energy that was already in the system or energy that is applied to the system. If the system is linear, right, we can understand the total response of that system to the combination, right, of externally and internally applied energy just by summing them up. We sum those two pieces up. And the only reason we can sum them up is because the system was linear. This turns out to be really powerful because the math needed to the zero input, right, is different. So the math here, right, is different than the math for the other part. By breaking up this total response into two pieces, each with their own math, we've divided and kind of conquered this understanding of this circuit, so that we can generate a solution, understand its behavior. Linear systems allow us to break it apart in a really logical kind of way as a consequence of where the energy came from, either initially inside the system or applied to the system. If you remember back to your differential equations, you probably did some solution to systems. The particular systems there you might have been talking about were differential equation, or systems that could be described by a differential equation. They probably broke their solution up into different pieces. They might have done something like a homogeneous and non-homogeneous solution, or they might have done a forced and a natural response. There's many different ways of breaking things up. Why do we break them up, and what allows us to break them up? The thing that allows us to break them up, this solution into sums of pieces, is a linearity or a superposition property. The reason we do so is because it gives us different insight, and maybe the math behind those different pieces is different. So it's breaking up a complex problem into a sum of simpler pieces. So going back to what we've been trying to get through on this first property, we're looking at this first property of linearity. Linearity is just a statement of superposition. It says that if I have a linear combination of inputs, right, it generates the same linear combination of outputs. In a graphical sense, linearity says that the system operator H, right, commutes with summing and scaling. We can interchange the order there. Here I had my summing and scaling, and I reversed the order to where it became first, and the system then became second. And if we can get the same result out of that interchange of order, we have a linear system. We also looked at this idea that linear system, because it allows for things like additivity, it gives us this sort of powerful technique in order to look at the response of a system as a decomposition of separate or smaller pieces. The reason that we want to do that is that those separate and smaller pieces might have different mathematical descriptions, or might be easier to solve in isolation rather than trying to solve everything at once. An example of that kind of decomposition is breaking up the total output of a system in terms of the outputs that are resulting from internally stored energy and the output that is a result of externally applied energy. The internally stored energy generates an output that is called the zero input response. So no input, just internally decided or described energy is going to generate that output. The zero state response is just the opposite of that. It has no energy inside the system, and it just lets the output reflect what the system does to an externally applied input. Take those two together, you can find the total response, something as far as describing the behavior of that system when it has both internally stored energy and externally applied energy through its input. A comment we might make is that even though linearity itself seems pretty straightforward, not every system has that. So we do need to check systems as to whether they have particular properties. In fact, to be totally honest, there's very few systems that are truly linear in real life. They almost always break when you put too big of an input on it. I would say that most systems, or many systems, let's go many, many systems, even though they might not be strictly linear, are at least approximately linear over regions of interest. So even if you have a nonlinear system, you can oftentimes still use that linearity type of an idea. We will get, after we've thrown out a couple more properties, to the idea of how we can either show or not show, prove or not prove these different properties. For the time being, let's just get the properties themselves out. So let's look next at something that is called shift or time. You could use either here, shift or time invariance. Shift or time invariance is second property, also one that is quite important for us. We will also sometimes just abbreviate this TI. That comes from the time invariance. So if I talk about a system being time invariant, I'll often talk about it being a TI system. If I want it to be both linear and time invariant, I might talk about an LTI system. And it turns out that's a designation we're going to look at a lot. There's another kind of name for this shift invariance or time invariance. It's also called the constant parameter. These are also called constant parameter systems. And hopefully, as we go through our description of this, it will become more clear why that is. So constant parameter systems as well. Basically, in a shift invariant or a time invariant system, right, a delay in the input, So a TI system is one in which a delay in the input, right, causes a corresponding delay in the output. This almost seems pretty intuitive because so many systems that we encounter in real life or in physical systems have this property of time invariance. If I delay an input, it just causes a corresponding delay in the output. We can state this mathematically in the following way. If an input x of t going through my system, right, generates an output y, right, then a TI system, a time invariant system, has what? It has a delayed input. Just take x of t and delay it by some amount cap t. So t minus cap t going through that same system will just generate a corresponding delay in the output. It will just give me that output y of t delayed by the same amount cap t. Thought of another way, much like linearity, could be thought about commutation between system and the operations of scaling and summing. This idea of time invariance says what? It says the system H, or cap H, right, commutes. It commutes with the shift, or you could think of that as the delay, right, operation. And this idea of commuting gives us a graphical way of looking at this. How might we do it? We might do it something like this. If I take an input x of t, right, and I run it through my system H, we know that that generates an output y of t. And then I'm going to take that y of t and I'm going to delay it by some amount. Delay. Oops, let's get that an actual delay. So delay it by some amount cap t. What do I get? I get y of t minus cap t. The commutability between system and delay says that we can interchange the order of those guys, right? And it shouldn't make a difference on the overall output of the system. So that would say something like this, that I have my input x of t going through now a delay, right? So now I'm going to go in here and run it through my delay first by some t. That would generate a signal that would be x of t minus cap t, just a delayed version of that input. And now we're going to run it through a system H, right? And that generates some output. So let's call that guy H acting on x of t minus cap t. Maybe I call that an output. I'm going to call it y prime of t, just so that we can not confuse notation. If these guys are equal, if they are equal, right? If these guys are equal, if they're equal, then we have a time invariant system. In other words, if it doesn't matter whether I system first and then delay or delay first and then system, if I get that commutability between system and delay operation, then I have a system that is time invariant. Okay, those turn out to be the two probably fundamental properties that we're going to be most interested in. We'll look at a few more before the end of the lecture, but for right now, let's go ahead and think about how we might show these, or at least look at different systems in the context of these properties of linearity and time invariance. Let me first make the comment that when you want to prove something, there's a couple things to keep in mind. Let's just say this as an aside of proving properties, proving or showing system properties. just making sure we're on the same page on this. If a property is false, if a property is not true for a system, so if a property is false, right, we can show this. We can show by finding, let's say, finding a single counterexample. What am I saying here? I'm saying you can prove something false through the application of counterexample. If you can find one case where something does not hold true on a system, well, then you know that it is not true. Finding one thing is enough, right? If a property is true, okay, if a property is true, we cannot prove it by finding a single example. We must show it in general. So in other words, the technique that we might use to show something false, finding a counterexample, is going to be inherently different than the way we might try to prove something true, because a single example of something holding true is not enough to guarantee that it holds true in all cases. So that is definitely something we'll want to think about when we're trying to prove or show system properties. If you suspect something is false, finding a counterexample, which is oftentimes the simplest thing to do, or it's very easy to do, might be the most expedient way to show that something is false, right? You find a simple counterexample and then you're done. However, if you have this idea that something is true, you do have to demonstrate that it is true for all possible cases. So let's look at a couple examples of systems and think about them in the context of linearity and time invariance. So this first example, right, I'm going to go ahead and think of a system like the following. I'm going to have an input x of t. I'm going to go ahead and let it get scaled by some amount. I'm going to call that m, and I'm going to generate an output y of t. Y of t then is just m times x of t. This is like an amplifier, right? So I've got an amplifier in here. If the size of m is smaller than 1, then it's going to make things quieter. If m is a factor that's greater than 1, right, then we're going to make something that is louder. And I might be interested in, is this system linear? Is this system time invariant? So if I looked at something like linearity, I'm going to just do that as a L. Is this a linear system? What do we start out with? We start out with that kind of given. If x1 generates y1, which will be just mx1, right? And x2 generates some output y2, which we know just by definition of our system is mx2, right? Then, and here we're checking, is, right, ax1 plus bx2 fed into my system going to give me that same linear combination of outputs? Well, this input, let's call this whole thing x prime, right, going into my system generates out an output y prime equal mx prime. But what is x prime? X prime is ax1 plus bx2. And if I just do a little algebra on this, I can write this as amx1 plus bmx2. What is mx1? That's just y1. What is mx2? That's just y2. So I can see here that y prime of t, right, the output in response to this linear combination of inputs is just that same linear combination of the original two outputs, ay1 plus by2. I've shown this regardless of what is x1 or x2. I've shown this to be true for any choice of x1 and x2, so we can conclude, yes, right, the system is linear. Something like that. How about time invariance? Is the system time invariant? Well, I know that some input x of t generates an output m times x of t, that is my output y of t. If I delay that, if I make a new input, call it x prime of t being equal to x of t minus cap t, what does that generate? It generates a y prime of t, which is equal to mx prime of t, which is equal to m times x of t minus cap t, right? Well, that also shows that what I've got here, right, is commutability of that system and the delay operation. A delay of my input, right, a delay of my input generates a corresponding delay. We hadn't quite finished that out. This whole thing, whoops, this whole thing was equal to, what is m times x anything? Well, that's just my y, but it was shown as being delayed, so this is y of t minus cap t. A delay in my input generates a corresponding delay in my output, so I can say yes, the system is time invariant. So I have a really simple system, an amplifier, and we can demonstrate through some basic logical math proof that it has both the properties of system linearity and the system of time invariance. So let's look at some slight modifications of this. Let's try the following. Let's take y of t, so this is the second example. Let's take y of t as being equal to mx of t plus b, something along those lines. So I have an input, it's going to get scaled, amplified, right? And then we're going to add to it another constant. So we're going to go ahead and let m and b both be constants. That's a constant and b is some constant. And I want to know, is this linear? And I want to know, is it time invariant? Let's start with linearity. Even though this equation reminds me of the equation of a straight line, I have some concerns. Maybe it's just a matter of some experience on my part, but I have some concerns about that constant being added out in front, okay? Or that constant being added out. Think about what would happen if I put an input of 0 in there. If I put an input of 0 in, what is my output, right? So if I went ahead and I said something like x1 of t equaling 0, what is generated out of that? That means y1 of t is equal to b. This is concerning, that I get an output without any applied input. Why is this a concern to me? Well, here's one idea. What if I create a new input, right? x2 of t equaling 2x1 of t, right? Well, 2 times 0 is still 0. 0 into my system, right? y2 gives me out b, but that is not equal to 2y, right? That is not 2y1 of t. So this thing fails, right? The scaling property, right? This thing scales the homogeneity property. Twice a input does not yield twice of that first input's output. So I've already shown that this thing is not linear. I found it not linear by finding a single example, and I even found a single example that just fails a part of the linearity. It fails the homogeneity. I haven't even checked additivity. All of that would be enough. I could stop right now. I could stop with that thing and know that I was done. If you were wanting to, you could do additional examples. You could also show that it fails under additivity, whatever the case may be, but a single example here is enough. So with this one counter example, I could say by counter example, right? By counter example, we see the system is not linear. How about the time invariance? Something like that. The time invariance on this guy. We had this idea that x1 of t feeding into my system gives me a y1. I probably don't need the ones there. Let's just go ahead and repeat what it was. It was an x of t going through my system gives me an output y of t being equal to mxt plus b. I'm going to now create a new input, x prime of t, being equal to x of t minus cap t, and I'm feeding that into a system. It's going to generate an output y of t prime, right, as being then equal to what? This guy is going to be my m, and I'm going to have x prime of t, right, plus b, which is equal to m x of t minus cap t plus b, which is y of t minus cap t. I've shown that a delay in the input, right, corresponds to creating an output that is just a simple delay, right? Delay in the input causes a corresponding delay in the output. So that's independent of what I chose for x. So yes, this is a TI system. We do know it's time invariant. So our very first example, it was both time invariant and linear. The second example, it was not linear but time invariant. Let's look at one more example, another quick modification of that first system. In this last example that I'm going to do here, I'm going to say something like this: y of t equals, let's do a time varying amplifier. So I'm going to let y of t be equal to tx of t, right? So here's something that gets louder and louder and louder as time keeps going on. So this is a time varying amplifier. The coefficient, the scale factor, right, varies with time. We could look at this thing in terms of linearity again. We can ask, is this a system that is linear? So I'd start out with something like this. If x1 goes to y1 and x2 goes to y2, then, right, what happens? What happens to a new input, call it x prime of t, being equal to ax1 of t plus bx2 of t? What happens to that when it goes through the system? I'm going to get an output y prime of t, right, the output to x prime, and it's just going to be equal to t times x prime of t. But what is x prime of t? X prime of t is ax1 of t plus bx2 of t. If I go ahead and do a little math on this, this is an a tx1 of t plus b, and I'm going to have tx2 of t. This first tx1 is just y1. This tx2 is just y2. And so what do I get? I get y prime of t. The output to this linear combination of inputs is just that linear combination of outputs, right? It's that same linear combination on the outputs. Because that's the case, right? Because a linear combination of inputs, because an input that is ax1 plus bx2 generates an output that is ay1 times by2, regardless of what is x1 or x2, I would say yes, right? The system is linear, no problem. And I did that in a general kind of proof. Now we could go ahead and take a look at that time invariance, right? What did we know? We had an input x of t, and it generates an output y of t being equal to t x of t. If I go ahead and look now at a new input, call it x prime, being equal to just a delay of this other guy, x of t minus t, feed that into my system, I get my output to that input, we'll call it y prime of t, and that's going to be equal to t times the input, x prime of t. And what is that guy? That is an x of t minus cap t. That's my yt prime. But that is not equal to, right, y of t minus cap t. For me to get a simple substitution, right, where I just replace t with t minus cap t, right, go ahead and take this expression for yt and just replace it with t minus cap t, right, we know that that guy would have to be a t minus cap t x of t. That's getting too crowded. Let me just move it down a little bit to the next line down. We know that that guy, right, would have been equal to t minus cap t times x of t minus cap t. That t parameter out front, right, ended up not getting the delay operator in the first. So commutability does not hold here. We can conclude that this is not time invariant. Now, in this particular case, I've demonstrated in this sort of a general way, right, that it is not time invariant. It could have also been demonstrated with a simple example. If you didn't want to go through the more generic kind of proof, you could have done it by a simple example. To just demonstrate that, we could even do that graphically. Let's try this out. Let's go ahead and look at a signal that is the unit step. So here is some x of t. It goes through my system, and what happens to it? That guy gets multiplied by t. So I'm going to get something that looks like a ramp function, right? So this is my y of t, something along those lines. Now, if I went ahead and I delayed that input, so here's an x of t minus 1, let's say it starts at 1, and I run that through my system and I see what happens in there, I'm going to just get that guy, that delayed unit step, multiplied by t. And what it's going to give me, right, is something like this. This is my, if I called that first guy, right, an x prime, this is my y prime of t, which is not equal to y of t minus 1, right? It's just not a simple shift of that guy, not a time invariant case. Here I would have been proving this not time invariant, so proving the property false by counterexample, found a single example where it did not hold. That would also be totally appropriate in this case. Okay, so what have we done? We've talked a basic definition of what is a system. We've looked at two really important properties of system, linearity and time invariance. What I'd like to do is go ahead and finish out by talking briefly about a few more properties. We'll give some examples as we go along with these, and then we'll conclude out the lecture. So how about this? An instantaneous system. We might also talk about this as being a memoryless system, both meaning the same thing basically. This one really is pretty simple. It just says that the output only depends on the strength of the current, just the amplitude, right, of the current input. No memory, no delays, nothing that would require any kind of memory in the system. Let's take a quick look. If we had y of t equaling what? M of xt, that was my amplifier. That is memoryless, right? Its output only depends on the strength of the current input. Output is equal to something that's only dependent on x of t. There's no delays, there's nothing that requires memory, okay? I might sit there and then get this idea that all I need to look for is just x of t's. And if there's anything that's not an x of t, maybe I don't have a memoryless system. Well, let's try that. How about this? Y of t equals m of xt minus 1, something like that. This could be a different system. Is this memoryless? First off, let's figure out what the system does. The first system was what? It was an amplifier, and it was a delayless amplifier. It amplified the input instantaneously, right, and put that larger or smaller value out as the output. This one amplifies, but it takes a second to do so. This is actually a pretty common kind of behavior that we would see in real systems too. They oftentimes have delay. In this particular case, we can see the memory, right? We see that the output at t depends on the input at 1 second earlier. That's memory, right? That's some memory in there. Therefore, it is not memoryless. Let me quickly show two additional examples that just illustrate that sometimes finding what these properties are, whether they're true or false, does require you to put in some thought. You can't just blindly apply superficial rules. So let's try something like this. How about this? Y of t minus 1 equals m of x t minus 1. And I want to know, is this memoryless? Yes or no? Well, I see something that has an x of t minus 1, which seemed to be enough in the last case, right? We saw something like that. There was that kind of an idea in the last case that seemed to be enough to make it not memoryless. We might think that this thing was also not memoryless. But take a look at it. The delay that's involved here, that t minus 1 on the input, is also present on the output. This system that I've drawn is actually 100% equivalent, right, to this earlier system. Those two guys are absolutely equivalent. It's just the time I'm calling t equaling 0 has been shifted in the second case. This one still says that whatever the output is at whatever time it is, t minus 1, depends on the input also at the same time. Those times there, right, are equal. So the output, right, at some time, call it t minus 1, call it whatever you want, only depends on the input at the same time and the input strength at that same time. So therefore it is memoryless. It is a memoryless system. Okay? Even though I've changed the frame of reference for my time, the output does not require past or future values of the input in order to find out what the output is. Let's look at one more. How about this? Y of t equals d dt of x of t. This is a differentiator. So this has an output that's equal to the slope of the input. We only see t's in here. We don't see any t minus 1s or t plus 1s or any other value of t. But I also know derivatives require memory. You cannot determine the slope of a line, right, from a single point. If I gave you a graph and I told you a function at some particular point and I asked you to find the slope, you wouldn't know if it came from a thing that was like this or like this or like this, right? A single point, the strength of that signal all by itself is not enough to derive or understand slope information. So even though this particular system, you don't see any t minus 1s, t plus 1s, there's no difference in there, it is not memoryless. And it's not just this simple, easy test at this point to be able to state that. We have to use our understanding of the system and the mathematical notation there to come up with this statement. It's not memoryless because slope, right? Slope requires, even if it's infinitesimally far away, it requires, right, more than just the strength of a signal at, right, strength of a signal at some point. That slope requires, the signal and its general trend, either left or right. So this one, not memoryless. A few more system properties that we can talk about then. There's also a property called realness, so we can talk about a system being real. A real system is one that if the input is real, a real system guarantees the output is also real, right? If the input is real, a real system guarantees the output is real. Maybe put a different way, if a system is not real, there is going to be a chance that a real input could generate a non-real output. So let's take some cases again on this. Suppose I had y of t equals mx. Oops. We're going to go ahead and make that mx of t. Is the system real? Is that system real? Well, I don't think we can answer this unless I know about m. If m is real, then yes, the system is real because we constrained x to be real and y would be real as long as m was also real. But if m was complex, right, if m is complex, then no, the system is not real. A kind of hint or thing to look for on realness is if those things that define or describe the system involve some j's in there, right, that they have a way of injecting perhaps that imaginary number, you can be a little more skeptical that a system might be not real. How about this one? Suppose I had y of t equaling x squared of t. I squared that guy. Is that guy real? Well, I think it would be yes. And why do I say that? I say yes because if I take a real number, I don't care what the real number is, that's my x, and I square it, it remains real because I know a real number times a real number is a real. So a real, right, times a real does go to a real. So we know that yes, because realness as a property starts with the assumption that you have a real input. And can we guarantee that the output is real? Well, sure. In this particular case, we can, because a real number squared is always real. Okay. By the way, this system is not linear. You could check that out. It is time invariant and it is memoryless. So if you're wanting to check your ability to prove or disprove things, you might run your way through those as well. How about this then? Y of t equaling the square root of x of t. So instead of squaring the function, I take the square root. We could ask, is this system real? I don't see any j's in this or anything like that, but I do know that if I take the square root of a negative number, and a negative number is still a real input, right? I would get an imaginary output. I'd get something that was complex. So no, the system is not. It is not a real system. Now we could try to go through some sort of generic proof. You could make some big logic in there, but why not just do it by counterexample? We could say x of t equals -1 generates an output y of t equaling j. Real input, right? Complex out. Complex out. I've shown by a single counterexample that this is not a real system. By counterexample, you can disprove something, single example, and be done. Great. Another system property, and one that we have to just be a little bit attentive to because it uses some language we also saw in terms of signal properties. And while related, they're not exactly the same. We can look at causal. A causal. This is the system property. Whether a system is causal or not non-causal. Here we're saying that the output, right? Output depends only on current and or past inputs. There's no dependence on future values. We can say that the system doesn't predict the future. That's all connected with this idea of causality. Causality actually, when we talk systems that have time as the independent variable, causality is connected as to whether that system can be realized in practice. We as humans have not figured out a way to predict the future, so we are not able to design or implement causal systems. So causality has a direct connection to whether something is physically implementable or realizable, something along those lines. So again, let's look at some very quick system examples. How about this? Y of t equals m of x of t minus cap t. This was that amplifier with delay. And I say with delay, assuming the parameter t was greater than 0, right? So if I was going to look at this guy and say, is it causal, right? I could say yes if cap t is greater than or equal to 0, because there we're just delaying the input. The output in any particular time would depend only on the input or a past input value. If it was a case where t was less than 0, then no, it would not be a causal system because that would require something in the future. For example, y of t equaling mx of t plus cap 1. We could look at it just simple case. Y of 0 is equal to mx of 1, right? And we could see there that y0 depends on input x, 1 unit of time in the future, right? So it could not be causal as a result. Causal systems cannot predict the future. Invertibility. So I could say, is the system invertible, for example? Can we recover the input exactly from the output? So in other words, can we recover the input from our output? So let's look at a couple examples again. I could have my y of t equals mx of t. This is my amplifier. If m is not equal to 0, then yes, it is invertible. How do I know that? because I can get x of t as just being 1 over m y of t. I can solve for x there, right? I can get back x by running it through an amplifier of the reciprocal scale value. The only case where this would not work is if m was 0, and that would be a boring system anyway. That would just say that the output was always 0, so it's not going to be something that's probably all that useful in that case. How about this one? This was one we looked at before too. Y of t equals t, x of t. You could again try to go through and just solve for x of t as an example. X of t equals 1 by t. Y of t, it seems like we can get that answer, but we do know t sometimes can be equal to 0. At t equaling to 0, we can't recover the input. So even though it's only not recoverable at a single point, this guy is not, right, invertible because we lost a single point of a value. Maybe you're not so worried about that 1 point, whatever, but that's really not the issue here. The issue is whether this thing is invertible, and invertible requires that you recover the input completely 100% from the output. One last one, and then we'll basically be done for today. Let's talk briefly about stability. We'll see later that there's different forms of stability. For right now, we're going to talk a particular form. We're going to talk BIBO, what is called BIBO stability. What does this stand for? This stands for bounded input, bounded output, bounded output stability. Stability. Bounded input, bounded output stability. Stability itself is generally an incredibly desirable property with systems. The idea is that we are given that the input is bounded. This is our given. Given that an input is bounded, is the output also bounded? And if you think about this as an idea of a system, bounded inputs are stuff we can generally make, right? We can make inputs that have a finite range of voltages or currents or whatever the case may be. And we definitely are interested in whether those nicely defined, nicely behaved signals generate outputs that are also nicely defined and nicely behaved. We don't want them flying off to infinity. A lack of stability generally means that you put some kind of nice input in and it blows up. It becomes unstable, it becomes unbound, it flies off in amplitude either plus or minus infinity. A well-defined input generates something that is very poorly defined on the output. Systems that are unstable generally break. Systems that are unstable melt boards. Systems that are unstable cause all sort of catastrophic failure generally. So stability is very important for us. We want to design for stability, and we want to ensure that systems are stable so that in a range of given inputs, it doesn't cause the system to break in its output. It doesn't cause the output to become unbounded. This bounded input, bounded output stability is a little bit tricky to demonstrate in all cases with the mathematics that we have now. We'll work on some additional techniques as we go, but let's at least look at a couple examples. We'll look at some simple ones. How about that amplifier again? Y of t equals mx of t. Is it BIBO stable? Okay, m is a finite real gain factor, right? It wouldn't make any sense to have a system that had an infinite amplifier. Okay, so that's not really in the realm of practicality. So we're talking a finite gain factor, and we're wondering, is this BIBO stable? What am I looking for? We're looking at mathematically something like this. If the input x of t is bounded, what does that mean? It means the magnitude of x of t is always bounded by some upper limit in size. It's always smaller than some finite number m of x, okay? So if the amplitude of x is finite, right? And that's true for all t, that there's some greatest and finite upper bound to its size, then we are looking for, is the output y of t also finite? Bounded input, so the first part is the if, is the bounded input, does it generate a guarantee in the bounded output? If we look at this, we can just go back to our definition. I'm looking at the magnitude of y of t, and I want to know about that. But I know y of t is just mx of t, right? Magnitude of a product is a product of magnitude. So this is magnitude m, magnitude x of t. But because of the if statement, I knew that the input was bounded. So magnitude x is always less than or equal to mx. So this whole thing is always less than magnitude m times a finite number mx. But m is also finite. So this thing, this thing is less than infinity because this is finite, right? And this is finite. And because magnitude y of t is less than infinity, we can conclude, yes, it is BIBO stable. We know that this thing is a BIBO stable. A regular old amplifier doesn't tend to cause things to just blow up. Let's look at one last one. How about this? Y of t equals d dt of x of t. This is a simple differentiator system. We can certainly try to build circuits that will do differentiators, but is it a good idea? Is it a stable system? Is it a bounded input, bounded output system? I'm worried about that differentiator. I know differentiators amplify high frequency noise. I know differentiators cause a large output in the presence of discontinuities. We saw that earlier, knowing that the derivative of a unit step, for example, creates a delta function, right, that has infinite output. So I'm going to do this by counterexample. Let's let the input x of t be just this. It's a unit step function. So we're going to let it be a unit step. I run that through my system. Y of t equals d dt of x of t, right, which is d dt of u of t, which is just delta t, right? We've seen that before. So that's going to go and fly off to infinity. This is bounded, right? This is bounded. This guy is not bounded. By counterexample, I see that this is not BIBO stable. Okay, brief summary and we'll be done for the day. This particular lecture has been focused on not signals, but systems. Systems are objects that operate on a signal to generate an output. These systems, right, have a variety of properties. These properties will prove useful in being able to understand the system behaviors and also to begin to more precisely explain things like input-output relationships. We've looked at a series of system properties. The two most important properties at this point were linearity and time-invariance. Linearity is commutation of the summation and scaling operations with the system itself. It's basically stated another way that the principle of superposition applies. Time invariance is also commutation. It's a commutation of delay in system operator. It basically says if you have an input giving you an output, well then delaying that input will just give you a delay in the output. We also looked at system properties of memorylessness, realness, causality, invertibility, and BIBO stability. All of these different properties of a system give us additional insight and information about that system so that we can go through and better analyze or design systems to behave in the ways that we want or understand their behaviors. Next time, we will complete Chapter 1. We'll run through something called operator notation, look at internal versus external descriptions, and make a brief statement about something called state space.